In this video, we explain precisely what it means for a matrix to be in row echelon form and reduced row echelon form. These are the forms for which it's very easy to read off the solutions to a system of linear equations. So the definition of a matrix to be in row echelon form is that first non-zero entry in each row is a 1. So let's look at this example here of a row echelon form. And let's look at the rows. And in each row, the first non-zero entry is a 1. There is some rows down here that have no 1s, and that's okay. Condition 2 says that those rows consisting entirely of zeros are moved to the bottom. Going back to condition 1, and in this example now, this says that this is not a row echelon form, but it does satisfy condition 1, that as you go through the rows, the first non-zero entry in each row is a 1. So we still don't know why this is not in row echelon form. We'll see shortly. Okay, and we talked about 2. Then in 3, it says if in any 2 successive rows that aren't all zeros, the leading one in the lower row occurs further to the right than the leading one in the higher row. So here I've highlighted the leading ones, and they're occurring further to the right. That's what does not happen in this example. This leading one is not further to the right of that row before it, and therefore, finally, we see why this is not in row echelon form. The echelon word refers to some sort of positioning, for example, of troops in a military where they're gradually moving to the right or something like this. So it might be a little difficult to remember exactly these 3 conditions, but just the general idea is we've got leading or pivot 1s, they're gradually moving all to the right, and the column below the 1s consists entirely of zeros. That's what's encoded in this condition 3, is that as you move to the right, the pivot 1s also move further to the right. Now, for a matrix to be in reduced row echelon form, in addition to the 3 conditions we just discussed to be in row echelon form, we need the additional condition that each column that contains a leading 1, these are the highlighted ones here, that every place else in that column is a 0. So in this example down here of a reduced row echelon form, if you look at this column, everything is a 0. If you look at this column, everything else is a 0. Similarly, everything else is a 0. Here's an example of a row echelon form that's not in reduced row echelon form, because in this column here, this thing here is not a 0. We can make it a 0 by doing an elementary row operation where we subtract off a little bit of this 1 to make this a 0. And so you can always get to reduced row echelon form from row echelon form by doing some additional elementary row operations. And then, once again, this column here has terms that are not 0. And by contrast, this column here, everything else besides the 1, the pivot 1, is a 0. A reduced row echelon form matrix can have some entries that are not zeros or 1s, like this one here. There's nothing to clear out. There's no 1 down here to be able to clear out that, whatever that thing is. And you can't use this one because you can't use column operations to clear things out. You can only use row operations. This is a slight bit of terminology. So Gaussian elimination is simply a recipe for starting with any matrix and getting into row echelon form by doing the elementary row operations. That's what we are doing in the previous videos where we talked about solving a system of linear equations by doing these elementary row operations. There were 3 of them again. And then Gauss-Jordan is a variant where you get to reduced row echelon form. And it's not important to remember which is which. They're basically the same idea of just repeatedly doing the elementary row operations to get to reduced row echelon form or row echelon form. Let's do an example. So here this question says, solve the system of equations, 3 variables. So as we've seen before, we convert to the augmented matrix. So this is 1x, 1y, 2z equals 9. So we've got 1, 1, 2, 9. I usually leave off the vertical line here that represents the equal sign. The augmented refers to we've added this column on the right-hand side of the equal sign. Sometimes, for various reasons, we'll leave it off, but okay. So now what we want to do is, we've got this pivot 1 already here, and we want to clear out the numbers below it to make them zeros. So we want to clear out this 2 and clear out this 3 to turn them into 0. So to turn this 2 into a 0, we replace this row by adding to it -2 times the first row. So -2 times the first row becomes -2, -2, -4, and then 9 times -2 is -18. I am adding that to the second row. So I've copied over the second row. Then I do the addition. -2 plus 2 is 0. That's the key point. And then I replace this row here as this new second row. Then similarly, I make this 3 into a 0 by replacing this row by -3 times the first row. That's what I've done here. I'll skip saying all the details, but you can pause the video or do it yourself. So now we've got a column that's all done, in the sense that we've got a 1 and we've cleared out the entries below it to get a 0. Then we move on to the second column. We can't do anything with this because that's tied up with this. We need to move on to rows below it. So what did I do? Well, I added row 3 to row 2. That will give me a pivot 1 in this spot. Again, there's many possible choices that you could do. You don't have to do what I did. And in the end, they'll all get back to the same reduced row echelon form as a final answer. Now that I have a pivot 1, I can use it to clear out this 3 and turn it into a 0 by replacing this row by adding to it -3 times row 2. Here's -3 times row 2, add it to row 3. This is going to be the new row 3. So that's what we have copied over here. And so now we've got these pivot 1s, and this is in row echelon form. It's not because the pivot 1s highlighted in green are moving towards the right. Now it's not in reduced row echelon form because we don't have zeros above it. We just above the pivot 1s. We just have zeros below the pivot 1s. But I decided to stop here because I was just essentially lazy and not continue doing these other steps, in part because continuing doing these other steps could lead to introducing some arithmetic errors. And this is good enough because we can easily read off the solution to the system of equations from the row echelon form. It's a little bit easier if I have the reduced row echelon form, but okay, this is what I did. So the first equation here, the first row here translates to the equation x plus y plus 2z. So again, x plus y plus 2z equals 9. I've left off the vertical symbol or line that's usually here, so I just have to remember it. Okay, then this is 0x plus y minus 4z equals -10. So that's this equation. And then this row here translates to z is equal to 3. So this one here, I immediately get that z is equal to 3. Remember, we're trying to find out what x, y, and z are. And then what I do is back substitute. So I know that y is equal to -10 plus 4z. I took this equation and solved for y by adding 4z to both sides. And then now I know that z is equal to 3, so substituting in 3 for this value of z, we get y is equal to 2. And now finally, we can solve for x. We've got x is equal to, from this equation, 9 minus y minus 2z. And we know what y and z are from the previous calculations. And so we get that x is equal to 1. So here's our answer. X is equal to 1, y is equal to 2, and z is equal to 3.